What I am going to be talking to you today about is climate change and species and how extremes are affecting the biota. And there's a lot of co-conspirators in what I'm going to be talking to you about today. A lot of people have contributed to this, and so it's a lot of their work. I'm just going to be reporting on it today. Before I talk to you at all about extremes, extreme temperatures, or any other kind of extremes, I want to talk to you a little bit about how animals work. And this is a very, very small community of canines. There's only the wolf, the coyote, and the red fox. So there's 3 species. And in the 1870s, around in here we have its relative abundance on this axis and time on this axis. So in the 1870s or so, we decided we wanted to eradicate the wolf. And we did a really good job of doing that. And we had one really strange surprise. The coyotes went up in abundance. So it was a complete surprise. Then we decided, okay, let's get rid of the coyotes. So we did a really good job of doing that. And now we had our second surprise. Up popped the red foxes. So the point of all of this is that here we had a very small community, just of 3 species. We had 2 interventions, and we knew exactly what those interventions were, what the forcing was. We were actually going to suppress different populations. And we had 2 huge surprises. Now, fast forward to today, and we have about 10 million species on the planet, and we are pushing them in ways with the climate that we really don't understand. So we don't understand what we're doing to them, and we don't understand how they're going to be reacting. And if one reacts, it's going to have a cascading effect on others. So the point of all of this whole slide is to say we have to expect a lot of surprises, and we're going to get a lot of surprises, and we're going to get a lot of extinctions too. So there's that issue also. Now, in California, we're very lucky in some ways. We have a lot of biodiversity. Some of it is in critical stages right now, and so this is partly saying how many species we have. It also is saying how many are vulnerable and endangered right now. But we do have our work cut out for us here in California. Now, we do know that species are already changing. They are not sitting around waiting. This is a pika, and it was one of the species that was looked at in the Grinnell project. Joseph Grinnell sampled this particular species along a transect up the Sierras back in the turn of the century, basically. And then Berkeley has gone back and looked at the exact same places for them and has found that indeed what has happened is there has been a range shift. And the species are all over the globe, not just here, but all over the globe. Species are moving toward the poles, and they're moving up in elevation. And the up in elevation can be seen here. In 1900, when Grinnell did this work, it was up to, as high as 7,800 feet. In 2004, when Berkeley did the reevaluation, it was up by 9,500 feet. So they really are shifting. This is just a really good example that you can see in California and how things are moving up, and they're moving toward the poles. So they are moving, and now we have, this is a plot of 60 different types of birds. It's only bird communities now, and it is in 60 years. And the thing is that as we have the species moving, and they're moving poleward and up in elevation, they're not moving together. Darwin said that all the natural communities are hooked together, and as one moves, all of them will move together. Well, we now know that's not true. One will move this way, one will move this way. They're both primarily north, but they're going different directions. One might move a lot faster than the other one. So we have a lot of breaking down of the biotic interactions. And this is what this slide is telling you. And what this is saying is in the bright red areas are where we're going to find species communities that don't have the same kind of composition of species as they do today. So now there are completely novel communities in these darker reds. So the red means they're more novel, the blue means that they're more similar to what we have today. So you can see that there's going to be a lot of changing going on. we really don't know how the species are actually going to be interacting very easily together also. So there's a lot of unknown in what we're talking about today. So what I want to do today is I do want to go through some extremes and try and put species into them, and so you can understand how they're going to be happening. So we have the heat waves, first of all, and then Tony just talked a lot about fire, and fire is a big one for species, so we'll talk about that. We also have to talk about cold snaps because that affects species an awful lot too. We are going to have fewer cold snaps, which in some situations is good, in other situations is not. Then I'm going to go on to drought, and something that I didn't realize with drought, but when you have drought, you don't have as much fresh water going out into an estuary. So now you're going to have saltwater intrusion, and it really makes a big difference to the species in the area. Then obviously we have floods, and then coastal upwelling also, which is also being seen as a real concern for species. So let's now first talk about the heat waves and the fires. These are two different groups of plants, the California lilacs and the manzanita trees and the like. This is where they actually are occurring in these two counties. And what they are obligate seed shrubs. And what that means is that the seeds themselves have to go through a fire before they can actually germinate and grow. And this has been going on for a very long time, and everything is working out fine. The thing that is of concern now is that we are actually having more frequent fires. And so what happens is the seed will go through a fire, it will germinate. It takes about 10 to 15 years to get large enough then to put out its own seeds and then have a seed bank in the soil. So when a fire comes along, then all those seeds are stimulated and then they start germinating. What's happening now, though, is that we're having more frequent fires. And this is an example. Now, the gray is showing what is happening now. And then what we're expecting in the future is actually to have the frequency of fires. They're shifting this way. It's getting shorter. And people are really quite concerned about the cycle going on here. And it could actually indeed cause the extinction of some of the species that really do rely on fire. So it's kind of counterintuitive. You think fire will be good for fire species. For a lot of fire species, it's not because they don't have the time to germinate. Now this is for a future that is warmer and drier. And then I want to look at a future that is warmer and wetter. And you think that it would be better. And it's not. It's actually a little bit worse, and the reason that it's worse has to do with the fact that when it's wetter, then the annuals grow a lot more quickly, and you have more timber, not timber, but whatever it's called, fuel, thank you, fuel around the grasses and the like to actually fuel the fire themselves. So here we have to worry about how fast the fire cycles are. Other thing with extreme heat is you can have breeding failure and you can have mortality. This occurred in the hot area, the hot time in May 15th and 16th of 2008. And this was out on the Farallon Islands, and there was a lot of nest abandonment. And the nesting, they already had eggs and some of them had chicks. All of the eggs and chicks were killed. Some of the parents actually did not leave, and they tried to stay and shade their nests, and the parents ended up being killed. So there is a real change that can go on with heat events for different species. And Louise talked a little bit about wines, but wines are greatly affected by heat also. It really decreases the grape quality themselves. It means oftentimes that the grapes have to be picked early, and that means the sugars are too high, so that is what really hurts the quality. And the other thing that it does is it increases the number of pests that are around, and so that's a concern. Now, the other thing, too, wine is also affected by cold snaps because it can kill the buds. It also decreases the seed set. And the early rains also decrease the seed set because it washes away the pollen. And late rains can increase the grape rot itself. So you really do have a lot of extremes that are affecting wines. So now let's go on and talk a little bit about cold snaps. And In some situations, it's going to be good because we're going to have fewer cold snaps. This is an almond orchard that's in bloom, and if there is a cold snap right now, the seed set is not going to be very, very good. So the fewer cold snaps we have for situations like this, the better it's going to be. But then we have species like this. These are the Santa Monica Mountains, and it turns out that the species here, this is sugar bush, this is sumac up here. I don't remember what these are, but anyway, they're different types of species. And what they are they're zonated on these mountain sides. And so these species occur down lower, these species occur up higher. The reason that they occur in these two different places is that the ones at the bottom are adapted to very cold temperatures, and the ones at the top are not. And as you're changing the heating, then you're going to actually be changing where these species occur on the Santa Monica Mountains. And this is just an example of looking at a leaf of the sugar bush and the laurel. The laurel is in red, and it's up at the top of the mountain. The bottom of the mountain is much colder, and it has to do with how the colder air sinking to the bottom. And you can see how much lower now the leaf is at the bottom of the mountain than it is at the top of the mountain. There's a real big difference here. And this is fine. Things can go on like this really very easily, and the plants can have adapted, and they can, even when it gets down to minus 10 degrees C for the leaf, the plant can still survive. The trouble comes when you add into that drought. This plot is just a snapshot of the mountains. It's a profile of the mountain itself, showing you that these species are up here and these species are down here. This is cold here. The ocean is actually here. This is distance from the ocean. This is just elevation. But when the sugar bush, which occurs down in this very cold site, when there happens to be a drought and it gets cold at the same time, that then causes a lot of dieback. So you have to have both of these things. The synergistic effects of these things are really quite concerning. Now there are species, this is called the desert dandelion, and on the x-axis we have the 3 days average of low temperatures after the first storm. So there's a storm, and then they calculate what the temperature was for the next 3 days. And this is for the germination of the dandelion itself. And you can see, basically, if it's less than 10 degrees C, it germinates much, much better than when it gets warmer. So here is a species that we're going to have trouble with as we start getting warmer, because it's not going to germinate as well as it does when it is cooler. So there's a concern there. Okay, let's talk a little bit about drought and saltwater intrusion. And there is a lot of saltwater intrusion that does happen. This is first about the drought. This is from the checker spot butterfly that occurred on Stanford campus, and it was studied. Paul Ehrlich studied it. He did a lot of work on it. This is at Jasper Ridge, which is shown right here. This is Jasper Ridge where the butterfly is. There's the butterfly. What they found is that with drought, it actually wasn't drought, it was just actually an increase in the variance. Again, x-axis is time, y-axis is precipitation here, here is increasing variance. As you go forward in time, the variability of the rains really changes. It's getting up much, much, much higher. And it turns out for the butterfly itself, when it gets much higher than around here, it starts having trouble because its host plants start having trouble. So there's an interaction that's going on between the host plants and the butterfly itself, and the host plants are the ones that are getting hurt here. But if you look at what happens to the population of the butterfly, these are two different populations, population C and population H, and you can see that around in 1965, both of them really did start declining. They declined, and now they are actually extinct on the Stanford campus, so they are no longer there. We're trying to get permission now to reintroduce them to see if we can get them back, but that's in the works. We're not sure that's going to happen. But again, this has to do with the increase of the variability, which is something we're going to expect in the future too. The Rufous-Crowned sparrow Mulgard did a study on the Rufous-Crowned sparrow and found that there was a lot of variability in the number of fledglings per pair that were coming off, given for different years. And they couldn't figure out why. And so what they ended up finally figuring out is if they look at precipitation, it follows almost exactly with what's going on. So why is precipitation important to a sparrow? It's not. What it's really important to is the grasshoppers that the sparrow eats. And so again, we have this biotic interaction that's going on, but it's really strongly affecting how many of these sparrows can actually occur in an area, or do occur in an area. And now let's talk a little bit about saltwater intrusion into estuaries. There are different stations. The yellow ones are looking at zooplankton. These are the little bitty tiny animals that are, you can see them almost with your naked eye, if you have your glasses on, at least if I have my glasses on. And then these are benthos stations that are having recordings done. And what they were looking at, this is an example of a little zooplankton. What they were looking at is what was going on as far as the species in these various locations. And this is a very, very busy map, or graph. But first, on all of them, we have year on the x-axis, and then y is all abundance. And the different scale, the scales are actually different. This is 1500, this is 250. So there is a difference. But the point that I want to make on all this, let's first look down here. These are the native copepods. These are the native zooplankton. And you can see that over time, the native zooplankton has actually dropped. And now if you look at all the rest of these squares, those are all alien copepods. And what we find is this is the time that there was a drought. There was a drought from 1976 to 77. And what ended up happening is that the saltwater intrusion was able to allow this particular copepod and this particular copepod to come in too. Then we had another drought that was in 87 to 95. That's shown here. That actually hurt this copepod up here. This one brought it in. This actually may have hurt it too, but this brought this one in too. So there's a lot of dynamics that are going on here. A lot of people said that this had to do with the ballast water that was being changed. The boats were coming in and changing the ballast water in the bay, and we thought that that's where these were coming from. It turns out, oops, I'm getting ahead of myself. I'll get back to the ballast water in a second. During the drought from 87 to 95, this one here, the worst time period was between 92 and 93, which I've drawn here. And you can see for 92 and 93, in came these different copepods, and this one down here too. So we have 4 different alien copepods coming in to the bay at that time period. Now let's look at the ballast. That was when the law went in for the ballast. So ballast was not changing the ballast out in the open ocean we thought would make a huge difference. It may in some species, and I don't know that. But for these species, it really didn't make the difference. What was the real important aspect here was the drought, and the drought was allowing the salt water to come into the estuary much farther than normal. So that had to do with the copepods. Now we also have these little, here's the biomass, and you can see that the native biomass was very high here, and then it dropped down and it dropped down again. Those 2 drops, again, go very nicely with where the droughts actually were occurring. So the droughts were really changing not only the abundance of the native copepods, but also the biomass of the copepods. Now also in the bay we have little shrimp. They're actually called little shrimp. They're little, but they're also little shrimp. We have native little shrimp, these are our native little shrimp, and they're called opossum shrimp, but they're little bitty tiny shrimp. And what has happened now is the shrimp that are really called little shrimp are alien little shrimp, and they moved in. That's a hard one to decipher here. They moved in at that drought, and what happened is it actually got rid completely of the native opossum shrimp itself. And now this is a problem because it turns out that the little shrimp are not as nutritious as the opossum shrimp were, and now that is having effects on the fish, and that is having effects on the fisheries. And then the ballast came in. I plotted that out for the ballast. Then the only thing left on this plot is this one right here, and this is for clams. And we have the native clams are in the bright blue, and the alien clams are in the pink or peach. And again, you can see saltwater intrusion really did hurt the native clams themselves, and again, it allowed the new clams to come in. So when we have droughts, extreme droughts, that's when we have to worry about different species coming in to our estuaries. So now let's talk a little bit about floods. Floods have huge effects on plants and animals. The most obvious one that it has impact on are the fishes, and these are all native fishes that we have in California, and they are the ones that really have the most value for the fisheries, and all of these are dropping in abundance regardless of climate change. It has a lot to do with the damming of rivers and on and on and on. I can talk to you about that later. But now what we do is we superimpose on top of this damage that's already happened or is happening, superimpose on top of that climate change, and you really do have a lot of species now that are in trouble. In California, for the inland fishes, and some of those are salmon, we have 122 native fishes in California. That's 71% of all of the fish, inland fish, which we have 172 of them. There are 43 that are alien, and then 7 that have already gone extinct in California. Now, if we look at which of these are highly vulnerable or critically vulnerable, that's the picture. So now we have, the blue is all of the natives, but now we just have 21 that are not in trouble. We have 101, or 83%, that are actually in trouble already right now. We have 35 of the alien ones that are doing fine. 18 of those are in trouble, okay? And then we still have the other 7 that are extinct. So now you superimpose onto this the fact that you're going to have floods, and floods brings in silting, and the silting can actually really quite damage the fish, the eggs, all sorts of different stages of the fish's life. And then the last thing I want to talk to you about is coastal upwelling. And this is a picture that just shows, the blue is showing you where the upwelling is, and here's the upwelling. And it turns out that climate does affect coastal upwelling, and this is an example. This is cumulative upwelling index. I have no idea what that means, but what they're doing is looking at the upwelling itself. But the point that's important here is they were looking at it from 1967 to 2004, and then they looked at 2005. So here on the x-axis is day of the year, and here is this cumulative upwelling index, whatever that means. These are for 2 different locations, but you can see how strikingly different 2005 was from the other ones, and that's a real concern. And we actually, I'm showing this to you backwards, we figured this out later, that it had to do with the upwelling. But the upwelling greatly affected this bird, which is the Cassin's Auklet. And in 2005, there was absolutely no young produced at all, 0. And in 2006, the same thing. The thing that is interesting is you can actually use the numbers of chicks raised by the Cassin's Auklet to predict how many coho salmon you're going to have, because they eat the same thing. So it's a nice index. You can actually use the Cassin's Auklet index to figure out about your salmon. So things to remember, extreme events are happening now. They're not something in the future. The species are having to deal with them. They can't go out and get air conditioners, so they have got to cope in some ways. So we've got to help them as much as we can. So we have to start preparing by being very flexible and using the past to help us understand what is going to go on in the future. We have got to start incorporating change into our planning that we have today. And we have to remember, too, that species do help to buffer some of the human exposures. So thank you very much for listening.